we're going to find all the quadratic equations with real coefficients such that 1 minus 2i is a root. Okay? Now, one thing we haven't talked about yet is the idea of a conjugate. Okay? If z is a complex number. Now, a complex number is defined as a plus bi. Now, a and b could both be real numbers. They could both be imaginary. Generally speaking, we make a and b real numbers. Okay, that way a is real, that's the real part of my complex number, and b is also real, but because it's with the I, that then becomes the imaginary part of my complex number. So I've got the real part, which is a, and sometimes we just say that's the real part, and then b is the imaginary part, okay, which we just show as being im. Now, with that, we can create what's called the conjugate. So the conjugate we write with an asterisk like this. Now, the conjugate is simply a minus bi. All right? And there's several things that we can do with that, which hopefully we'll look at here in just a minute in a different video. But for now, we have this idea of, we know that one of the roots is 1 minus 2i. Now, hopefully you remember in the previous videos, anytime I ended up getting a complex number, it's because it was from the square root, right? The square root in the quadratic formula, or the square root when I'm solving an equation, when I square rooted the negative number, it gave me the I. And because I square rooted it, I always ended up with a plus or minus. So what's going to happen is that every single time you have a complex root, the conjugate will also be a root. So the conjugate here is 1 plus 2i. So if 1 minus 2i is a root, that means that 1 plus 2i also must be a root, because you had to get the plus or minus of the imaginary part there. All right? So what we're going to do is we're going to say that these two are the roots. Now, you should know that a quadratic equation could look like this. Y equals a times, if I have the roots, it's usually something like this, x minus alpha and x minus beta. All right? So with that information, I can go y equals a times x minus the first root, which is 1 minus 2i, times x minus beta, which is 1 plus 2i. Now, there's multiple ways that you could work this out. You could distribute the minuses and then do a trinomial expansion. What some people like to do is they like to just kind of leave it the way it is, and then we go x times x, which would be x squared. X times that would be minus x times 1 plus 2i. And then this times that will give me another minus x. This one would be 1 minus 2i. And then when I multiply those two together, I'll get a positive. And then it'll be 1 minus 2i, 1 plus 2i. All right? Now, at this point, I do still have this a hanging out here in front, so don't forget it. And we can now simplify. So I'm going to have x squared minus x minus 2ix minus x plus 2ix. And then here it'll be 1 times 1 will be 1. 1 times 2i will be plus 2i. 1 minus 2i will be minus 2i. And then negative 2i times 2i will be 4, and because I times I is I squared, then the negative will become positive, so positive 4. I go through and cancel out anything that I can, negative 2ix and positive 2ix, positive 2i and negative 2i, and my final answer is a times x squared minus 2x and then plus 5. You'll notice that we're able to write our quadratic equation with only real coefficients. That will generally be the case, is that a polynomial will have real coefficients. The roots can be complex or imaginary, but the equation itself, we will deal with real numbers. All right, so there's our final equation, and that's the end of that question. Let's move on to one last one. Okay, this is the last question we'll be looking at today. We're going to find the exact values of a and b if root 2 plus I is a root of this equation right here. So I've got the two roots because I know that root 2 plus I is a root, therefore root 2 minus I must also be a root. With that, I can write my equation. I can go x minus root 2 plus I and x minus root 2 minus I equals 0 because it's a root. Now, in this case, I don't need, remember in the last video I had an a here. In this one, I don't need that. That a is the coefficient which will end up being the leading coefficient on the x times x. We notice here that I'm going to get x squared no matter what. X times x will give me x squared. So really, there shouldn't be a coefficient this time. All right? Now, from here, some of you may actually know about the sum and product of roots. If you've done that, then you can simply use the sum and product of roots to get b and a because that's related to the a, b, and c as far as the coefficients of the quadratic. My students, not all of them have learned this yet, so we're going to go ahead and deal with this the same way as the last question. I'll go ahead and do this the other way so that you can see what it would look like. So x minus root 2 minus I, and then x minus root 2 plus I. You can expand this in the same way as we did the last one, or you can expand it this way. So x times x would be x squared. X times root 2 would be minus x root 2. X times I would be plus xi. Then I move on to the negative root 2. Negative root 2 times x would be minus root 2x. Negative root 2 times negative root 2 would be positive root 4. Negative root 2 times I would be negative root 2I. And then on to the negative I. So I'll have a negative ix. I'll have a positive root 2I. And then I'll have a negative I squared, which will be plus 1 because I squared is negative 1. Go through, eliminate what I can. So it looks like I've got a minus 2I and a plus 2I, a plus xi and a minus xi. And so it'll leave me with x squared, and then I've got 2 of these negative root 2x's, so minus 2 root 2x. And then root 4 is 2, plus 1 would be plus 3, and therefore I have the exact values of a, which would be negative root 2, and b, which would be 3. All right, that's all for this video, and I hope that you find it helpful.